Hi everyone. So in this video we will start talking about chapter 16, which will essentially cover the topics of superposition of waves. We'll talk about beat frequencies and how standing waves are formed, and we'll discuss different kinds of standing wave patterns, for instance, in pipes and strings. Okay, so superposition principle. This is actually a very general principle in physics. The principle states that two or more um, physical parameters that have that have linear responses can be added together to find the net response. So this is sort of a bunch of words, but the idea is quite simple. So for example, you've seen superposition principle already. If you remember when we started talking about rotational dynamics. So in rotational dynamics, we said that a general rotation is sum total. So a general rolling motion, for instance, has two parts. One is rotation about center mass, and the second one is translation of the center mass. So this is an example where the translation is a linear response, rotation about the center mass is a linear response, and you can add these two together to get the general rolling motion, right? Now we're going to use this principle, the principle of superposition, very extensively in the case of waves. So it turns out that for waves, when you have two different waves, the wave functions can be added together. So wave functions. So for waves, wave functions are linear responses. Okay, so since wave functions are linear responses, superposition principle tells us that they can be added together. So what does that mean? Okay, so what I'm going to do over here is I'm going to talk about two different interfering, overlapping traveling waves. So, in these equations, I've written out different kinds of traveling waves. So let's start with that. Over here, I'm going to go over to my notepad and talk about traveling waves being superposed, right? Superposition of traveling waves. So a quick example of a traveling wave is if I write y of x comma t is equal to a sine kx minus omega t. Okay, and just to remind you, this a over here, that's the amplitude of the wave. K is called the wave number, and omega, we refer to omega as the angular frequency. Okay, so this is one wave. Now I want to talk about the interference of this with another wave. So let's call this first wave y1. So the second one is going to be y2, y2x comma t, and that one is now a sine kx minus omega t. So roughly the same wave, except now I'm going to add in an additional part, and this is going to be our constant phase. And in this case, it's a constant phase difference between, so it's the difference between the two phases of y1 and y2, right? So y1 has no extra constant phase, y2 has this extra constant phase delta. All right, so let's talk about what happens when we take these two traveling waves and superpose them. So the superposition principle tells us that y of x comma t, when both of these waves are acting together, would look like y1 of x comma t plus y2 of x comma t. Okay, so that will be equal to, now I'm just simply going to add the wave functions. So I have a sine kx minus omega t plus a sine kx minus omega t plus delta. All right, so we're adding these two together. I can factor out the a, and so I have sine of kx minus omega t plus sine of kx minus omega t plus delta. Okay, and now I will use a trig identity to do this addition. So we know that sine of first angle theta 1 plus sine of another angle theta 2. In trig, this is given by 2 times sine of theta 1 plus theta 2 divided by 2 multiplied by cosine of theta 1 minus theta 2 divided by 2. So on this next line, we're just going to apply this formula, this trig relationship, and we will get a times 2 times sine of, and here we'll add the two arguments, kx minus omega t and kx minus omega t plus delta, and divide this by 2. And then we'll also have the cosine part, so cosine of kx minus omega t minus kx plus omega t minus delta divided by 2. Okay, so we can simplify this a little further. 2 times a times sine of, so the kx minus omega t repeats over here twice, and when we divide by 2, that 2 will cancel, so we'll get kx minus omega t plus delta over 2 multiplied by cosine of negative delta over 2. And that's because if you look inside these square brackets, the kx cancels with the kx, the omega t and omega t plus and minus, these cancel, so we're left with negative delta over 2. Okay, we can further simplify this as and write this as 2 times a times cosine of delta over 2 times sine of kx minus omega t plus delta over 2. All right, so this clearly is also a traveling wave because it has this kx minus omega t part. So that's our sort of the traveling phase of this wave, right? But this has an additional interesting feature. First of all, it looks like the amplitude. This is the part that is independent of x and t. So this is the full amplitude of the wave, right? The amplitude changes as delta changes. In particular, so the amplitude of the wave is now, amplitude is 2 times a cosine delta over 2, which means that if delta equals 0 or 2 pi or multiples of 2 pi, then the amplitude is 2 times a, because as soon as I put in delta equals some multiple of 2 pi, this cosine delta over 2 is going to be just plus or minus 1. So the factor of negative will not matter. The amplitude is simply the magnitude of this quantity. So I should have written this. So the magnitude of that quantity is the amplitude. And this amplitude is going to be 2 times a, because cosine delta over 2 magnitude of that for delta equals 0, 2 pi, etc. is just 1. Okay. What if delta equals pi, 3 pi, etc.? Well, in that case, cosine delta over 2, which is cosine pi over 2 or cosine 3 pi over 2, those are 0, which means that the amplitude then reduces down to 0. Okay, so that's the interesting thing. So this tells us that that there are two interesting kinds of um, interferences. So the first kind is a constructive interference. So this constructive interference happens when the phase difference between the two waves, remember this constant phase difference delta, when the phase difference delta is some multiple of 2 pi. So it's either 0 or 2 pi or 4 pi, etc. For a constructive interference, the amplitude actually adds up. So the amplitude of the two interfering waves adds up and gives us 2 times the amplitude of the interfering waves. We had amplitude A and A, so the net result is an addition of the two amplitudes for a constructive interference. Now there's another kind of interference which is this destructive interference. And of course, destructive interference happens when delta is some odd multiple of pi, so pi, 3 pi, etc. And there, for destructive interference, at the amplitude of the wave goes to 0. Okay, so this is sort of an amplitude analysis for the waves. Let's actually take a look at what these functions look like. So here I have plotted the two functions that I was adding earlier, and I have particularly plotted them for time t equals 0. So in the y direction, it's y x comma 0, and in the x direction, it's just x. And you see how the red and the blue curves interfere when the phase difference between them is pi, delta equals pi. They interfere and they give rise to a waveform that is just exactly equal to 0 everywhere, right? So that is the example of our destructive interference. And for constructive interference, I can just play this video. So this essentially, it's showing you how the interference is changing with delta. And we get through the constructive and destructive interferences. And this is the example of a constructive interference where we have both of the two curves, the original curves exactly match each other, right? Because the phase difference is delta equals 0 or 2 pi, etc. So they're exactly the same curves, right? And so the sum total of the two curves is essentially this bigger purple curve over here, which has twice the amplitude of the original curves. All right, so that's our discussion about superposition of two traveling waves. The next topic that we are going to address is beat frequency.